Hello, Wolfram.
Ja. Stefan, hörst du mich jetzt?
Ja.
Okay, sehr gut. Okay. Good afternoon, everybody. I would like to start with a short announcement concerning the assembly of the magnetic field sensor project. So the dates for this will be Monday, the 7th and the 14th. So I propose that on Monday, the 7th, Group B will do the assembly. So this date then will replace the simulation exercise of Friday, the 4th. So this will be all of Group B plus 2 members of Group A who were not available on in the following week. So we'll do this in 2 sessions, one starting at 1 and the next one starting at 3. And maybe we can decide during or after today's practical exercise who goes to which time slot. And then for Group A, the assembly session will be in the following week, which replaces the exercise of the 11th. And there we need only one session from 1 to 3. The practical exercises here in the PK room will just continue as normal. So if this doesn't work for you, please get in touch with us. Okay, so today we switch to a different type of transistor. So the last 2 or 3 weeks we dealt with the bipolar junction transistor. Today we look at a new type of transistor, so-called field effect transistor. We start with the structure and the principle of operation, and discuss the IV characteristics of these devices, and then move on to circuits, look at the circuit symbol and the small signal equivalent circuit, and also the high frequency behavior for which we need to understand the capacitances. And then we'll go through some application examples and finally switch to CMOS, one of the most important, or in terms of numbers of transistors, most important application of these transistors. Okay, so the cross-section of a MOS transistor is shown here. This is a so-called MOS structure. In this case, it's an NMOS. There are 2 types as for the bipolar transistor. So there's the p-doped silicon bulk is shown here in blue. And inside of this bulk, there are 2 highly n-doped regions, left and right, which are called source and drain for reasons that will become clear later. And over the area between the 2 contacts, between source and drain, there's a conductor, which is separated from the bulk by a very thin insulator layer. So the name comes from versions of this technology where this conductor was made from metal, and then this insulator was silicon oxide, and then at the bottom you have silicon again. So MOS is for metal oxide silicon. The name is often used, although these materials in many cases are different today. Sometimes more correctly, this type of transistor is called an IGFET, or insulated gate field effect transistor, but not many people use this acronym, and we'll just call it MOS transistor here also. So the electrical connections of these are shown here. So the substrate and the n-doped regions all have their individual contacts, as well as the gate. The p-doped substrate must be on the lowest potential of all of them. Otherwise, you have diodes between the N and the P that would be conducting. So these 2 diodes here from the source and drain to the bulk must always be biased in the reverse direction, in contrast to the bipolar junction, where one of them is always in forward bias. So here they must both be in reverse direction, and then we have small depletion regions around source and drain. So if you look at this from the top, not at the cross section, the cross section is at the bottom. You see the same thing drawn from the top. So you have the bulk in which everything is embedded, and the gate covers the region between source and drain. And usually these 2 are doped in one go. And the gate is applied on top of this region and covers the gate during the implants, when the implants are made. So that forms this structure here, where you have source and drain separated by an undoped region in between, where you still have the p-doping from the bulk material. And then one also needs a body contact here, which is usually done with a highly doped P implant. So the gate oxide under the gate, so the oxide between gate and bulk is extremely thin, down to angstroms in some cases, while everything else is usually covered with a much thicker oxide to protect the circuits. So let's start to look at how this works. We start with the MOS structure in an off state. So we have no voltage applied anywhere, so everything is at the same potential, which we can think of as being 0 at the moment. So now we have negative mobile charges in source and drain, just from the fact that they're highly doped. We have some positive charges in the channel, less than in source and drain, because the doping is weaker, but we do have mobile charges here. But there's no conduction between source and drain because of the junction fields that keeps the charges from going in and out. So strictly speaking, this is not the state that you have when the gate voltage is equal to the bulk voltage, because these are different materials, so we have a slightly different work function. But that can be ignored for our discussion here. So the next thing is that we raise the gate voltage a little bit, and then this will push away the positive mobile charges here that come from the P doping. And if we push away enough of these charges, the region here under the channel becomes depleted. So the ionized acceptors will still remain here. They cannot move away, so they will still be in the channel and put some charge there. But we'll also get an increasing number of mobile negative charges that are thermally generated. And in equilibrium, we know from the diode discussion that the product of the two is constant. So if we remove positive charges by applying this positive potential at the gate, then we start also accumulating negative charges here. But the first step is to go into depletion. Only if you increase the voltage further and go beyond a certain threshold value, which we call V threshold, you start seeing more electrons than holes in this region, and you start getting what is called inversion. So once you have more electrons and holes, this is called inversion. And when you go even beyond this point, you go into strong inversion. And now you have a sheet here of mobile electrons, and the density of these charges grows linearly with the gate voltage. So according to this, so that the total charge can be expressed in terms of the capacitance per unit area of this structure multiplied by width and length of the gate, and the difference between the gate voltage and the threshold voltage. The threshold voltage, which is sometimes also written as just VT, I'll call it VTH here, so for threshold, because it should not be confused with the thermal voltage VT. This is something completely different. It depends on that, so it's also dependent on temperature, but it contains the effect of the work functions but also the doping, so the remaining charges that are sitting here, and also possibly later the bulk potential. But for the moment, we can just take it as a value that characterizes the structure, and you have to go beyond this value with your gate voltage to start accumulating mobile negative charges here. Now, now we are in this state of strong inversion and start applying a slightly different voltage between source and drain. So the difference is small, much smaller than the inversion voltage, so much smaller than the excess of the gate voltage over the threshold. So that means that whatever we do here has negligible effect on this conducting layer of electrons. Then this layer here will just behave like a conductor or a resistor. So if you have a small voltage difference here, then you will have a small current that flows either from the left to the right or from the right to the left. And the current is proportional to the voltage difference between source and drain. So this mode of operation is called a linear region, or sometimes region. So if you look at it in an IV curve, so here you have the drain source voltage and then you have the drain current, then it follows linearly. So, and the resistance of this channel is controlled by the gate voltage. So if you go higher with the gate voltage, you get more charges. So the resistance of this sheet becomes smaller. So you get a higher current here. Now we start increasing the voltage more. Let's restrict ourselves to the case where the drain voltage is higher than the source voltage. And in this domain, we have charge carriers that flow from the source to the drain, so electrons in this case. So that's where the names come from, of course. So electrons flow from the source to the drain. Now, if you increase this current, you start developing a voltage drop here. So this is basically like a resistor, and if you have a lot of current, then the voltage will change along the channel, basically going from the source voltage to the drain voltage. This, however, has the effect that the effective voltage difference between the gate and the channel changes along the channel. So it's higher here than it is here. So this will then reduce the conductance here. So the resistance gets higher. And as an effect of that, the total current is no longer simply proportional to the drain source voltage, but as the drain source voltage changes the resistance, it falls below this linear extrapolation. So now what you get is a current that turns over and deviates from this linear behavior. This can then be described as having an x-dependent potential in the channel, where x is the coordinate along the channel from source to drain. And we'll later look at this voltage here as a function of this x. So here it changes from being 0 in this case to the drain potential over here. And as a consequence of that, you also have a x-dependent charge and conductivity. So let's look at the density of mobile charges first. So this is the case that we had before when everything is at the same potential. Now, if we have an x-dependent voltage here in the channel, so we can chop this into pieces, and every piece has a certain smaller amount of charge. So we replace L by delta X now, if delta X is the width of this segment, and the effective potential is no longer V gate, but V gate minus the Vx, which is the potential in the channel. And then dividing this by delta X and going to a differential here gives us the carrier density, which is then the oxide capacitance per unit area multiplied by the width of the channel and this difference here. Okay, so now we can use these charge densities and the voltage as a function of x to find the current from source to drain. For this, we need the mobility of the carrier. So mu e here is the mobility of the electrons. So the mobility of electrons at the surface, to be precise. And the current is then mobility times charge density times the lateral field, so the field along the channel. It's not the field between the gate and the channel, but this is the field along the channel, so perpendicular to the direction from gate to channel. So this is, of course, simply the derivative of the potential with respect to x. And for the charge density, we can plug in the formula we had before. So we end up with electron mobility times channel width and channel capacitance per unit area multiplied by the difference of gate voltage minus threshold voltage minus local voltage minus local channel voltage times the derivative of the local channel voltage. So to go on from here, we note that charge conservation tells us that this current must, of course, be constant. So there's no charge flowing in and out of the channel to the top and the bottom or so. So this, the left-hand side here is just a constant, which we call the drain current. Further, we note that an expression like this here, if you take y for the voltage, then is like constant minus y times y prime, where prime is the derivative, which we can write as a times y prime minus y times y prime. And this is then the derivative of a times y minus 1/2 y squared. So, which means we can easily integrate this expression, and we can obviously also easily integrate that expression along the channel, which we do here. So the integral of I of x times dx from 0 to L, so from the source to the drain. On the left-hand side, on the right-hand side, this integral. Since we know that this is the derivative of this expression, we can simply write drain current times L is this expression here, which we evaluate for the voltages at the source and the voltage at the drain. And we take the source voltage to be 0 in this case. This is done here. So drain current times L is the mobility times width times capacitance times this expression. So for 0, this becomes 0. So we simply have the drain source voltage here. So now we have the NMOS drain source current as a function of the gate voltage and the drain source voltage for not too large drain source voltages. So one should just note that this is obviously proportional to the transistor width, which makes sense. So if you make the transistor twice as wide, you get twice the current. It is inversely proportional to the transistor length. So shorter transistors give you higher currents. And it's also proportional to the carrier mobility. So in this case, it's mu E for the NMOS, but it will be the whole mobility for the PMOS. So similar to the situation with the bipolar transistor, we will have that when you have transistors of equal geometry, then the NMOS will be stronger than the PMOS. Okay, so if you plot this curve as a function of drain source, so here the drain voltage, here the drain source voltage, this is basically a parabola. It starts at 0 for no drain source voltage, and will reach a maximum and will eventually turn over. So we will discuss whether this turnover happens later. But let's first look at the maximum, which is, of course, when you have the derivative with respect to the drain source voltage here, you get this expression. Yes. So these constants, you have, what am I doing here? Yes. So and this becomes 0 when the term in the bracket is 0. So when we have a drain source voltage that is equal to the difference of the gate voltage minus the threshold voltage. And this is called the saturation voltage. And the corresponding current is what you get when you plug this voltage into this formula. And then you get simply 1/2 times the mobility times the oxide capacitance. And then again, the ratio of W over L. And now times V gate minus V threshold squared, because here you plug in V gate minus V threshold here. So you have the squared here, minus 1/2 the squared there. So you get 1/2 the squared here. Okay. So if you look at where these saturation points are for different gate voltage, then you find that these lie on this parabola where you have on the horizontal axis the saturation voltage, and on the vertical axis the corresponding current, which is K times the saturation voltage squared. So this is this you'll see sometimes now in other slides, that this saturation point lies on a parabola in this kind of plot. Okay, now let's look at what actually happens when we reach this saturation. So we said the current maximum is reached when the drain source voltage is V gate minus V threshold. And in this case, the channel charge, which is given by this expression, when you evaluate it at the drain, so you plug in, what am I doing here? Right. So when you plug in the drain source voltage here, so you get V gate minus V threshold here, then this term becomes 0. So this means that the density of charges at the source is going to 0 when you reach this this point of saturation, and this is called pinch off. So it means the carrier density here really goes to 0 in this idealization. Now, if you go above the pinch-off point, then it means that the inversion charge in the channel is almost unchanged, but the electric field between the end of the channel and the source and the drain increases. So if you plot the voltage, so it goes like this. You have this increasingly steep curve here, and then at here it just jumps to the source voltage. However, the current will not change because the inversion charge in the channel does not change. So the current that flows through this remains constant. So you can in an analogy of a waterfall, when away from the edge of the waterfall, you have a current with a certain water level, so to speak. And then as you get closer to the edge, the height, the depth of the water decreases, but the speed of the water increases, and then it falls over the edge. And at the edge, the depth of the water is basically zero. It's very small. It's not exactly zero, of course, because the water cannot flow infinitely fast. But the same is in some sense true here. So the charge going to zero is a bit of an idealization because the charges cannot move infinitely fast. But this is a good picture of what happens. And then once you reach this, it doesn't really matter how far down you fall here, the current will remain constant. So this is shown in these curves here. So once you reach the saturation, the current will no longer increase anymore. This region is, of course, therefore also called the saturation region here, where the currents are constant. The behavior of this transistor in this region is similar to the active region of the bipolar. The physical mechanism is, of course, very different. Here you have majority charges that are pulled over by the electric field, while in the bipolar transistor you have the diffusion of minority charges. Unfortunately, the bipolar transistor also has a saturation region, which is something very different, which is more like the linear region of the MOSFET here. So you just have to get used to that, I'm afraid. We can look a little closer at what happens when you go above the pinch-off. So we said the voltage increases and then to the pinch-off voltage, and then makes a jump to the source, to the drain voltage. However, there's another effect. If you increase the drain potential more and more, then the depletion region around the drain becomes larger, which makes the channel effectively shorter. So the pinch-off point moves a little bit towards the source. However, the field that carries the charges from the pinch-off point to the drain is still there. So the effect here is similar to what happens in the base collector diode of an NPN transistor. So what this does is it reduces the effective channel length. So your channel becomes shorter, and hence the current will increase because the current is proportional to 1 over the channel length. So this is then again parameterized similar to the early effect of the bipolar transistor. It's called early effect also for the field effect transistor by this linear dependence of the drain source voltage minus the saturation voltage. And this is called channel length modulation. So instead of being flat here, you get a small increase as a function of the drain source voltage. This effect is, of course, much stronger when the channel is shorter anyway. So if you have a very long channel, it doesn't matter that this changes a little bit. But if your channel is very, very short, then this has a significant effect. On the other hand, once you have very short channels, there are many other important effects that we will not go into here. You have very high fields, for instance, in this region. In the idealization, the field has to be infinite here to really transport current with zero charge. This doesn't happen because the velocity of the charge carriers is finite. At some point, it's no longer proportional to the field, but it'll saturate, and this also leads to a deviation of your currents from this behavior. But we'll just stick with the idealized version here and look at the first or the most important small signal parameter, the transconductance. So GM is the modulation of the drain current by the gate voltage. So this picture here we've already seen. It shows how the saturation current behaves as a function of the gate voltage and the drain source voltage. So as a function of the drain source voltage is constant here. Now, if you look at the saturation currents here as a function of the drain of the gate voltage, you also get this quadratic behavior here. So there's no current when below the threshold, and then above the threshold you get this quadratic behavior with some constant in front of it. This is shown here. And Gm is of course simply the derivative of this with respect to the gate voltage. So you get mobility times oxide capacitance times W over L, and then gate voltage minus threshold voltage. So the thing to note here is that this grows linearly with the gate voltage. So if you increase the gate voltage, you increase your GM, which is an important parameter for amplifiers, for instance. Or you can, if you need higher GM, also increase the drain current, but it only grows with the square root of the drain current. So that's not terribly steep. If you remember that for the bipolar junction transistor, you have the exponential behavior of the current. So here, what is quadratic here is an exponential curve in the bipolar transistor, much steeper, and there you get now a GM that is proportional to the current, to the collector current, not just the square root of the collector current. So in some sense, the bipolar transistor has better analog performance here, but the field effect transistor has other advantages. Okay, so now we come to the circuits with field effect transistors. So let's look at the symbol. So this is in principle a common component with 4 terminals instead of the bipolar transistor, which only has 3 terminals. So now we have drain, source, gate, and bulk. The bulk does not play such an important role as drain, source, and gate, but it must be handled properly. So, for instance, it must never be more negative. Sorry. It must always be more negative than source and drain. Sorry, that's wrong. It is therefore often connected to the source that is shown here. So maybe I should discuss these symbols first. So these are this is an NMOS. The direction of the arrow here distinguishes NMOS and PMOS. So the gate is shown here, symbolizing this metal gate, which has no contact to the channel. And in some cases, the gate is not drawn in the middle, but it's offset to the side to indicate where the source is. In this case here, you have no way of distinguishing drain and source from the symbol itself. Sometimes people choose to draw the symbol like this, and then the side where the gate is offset to is where the source is. So the bulk is in principle an independent connection. It must not be, as I said, more positive than drain or source, otherwise the junctions conduct. So one way to prevent this is to connect it to the source. Another way is to always connect it to ground, which or the negative supply voltage in your circuit. And then when you do that, the bulk connection is often not shown, and you just have a symbol like this. The complementary structure, where you basically no, this is wrong again. You have an N implant. So no, sorry, you have a P implant. That's correct. So P implants on an N bulk. That is called a PMOS or a PFET. So the symbol here is different from the NMOS in the direction of the arrow here. So for both versions here, one where the gate is in the middle, one where the gate is offset towards the source. And here, if you want to connect it to the source, then you must, of course, connect it to the higher potential here. And the symbol without the bulk connection is drawn here with a little circle here, which is like a logical knot in many logic gates. So the difference between these two symbols is this small circle, which allows you to distinguish the NFET from the PFET. Okay, so a wide range of field effect transistors exists. So that goes from very small transistors in integrated circuits. They're usually in the planar technology, and the channel is lateral, so along the surface, with channel length from less than a micrometer, or from micrometers down to nanometers now in modern technologies. The currents here are typically in the milliamp to microamp range, and the threshold voltages are in most cases less than a volt. So the supply voltages for these processes are also rather low, 5 volt for larger technologies, down to less than 1 volt in more modern technologies. On the other hand, you have these power MOSFETs, which are also in a planar technology, but usually have a quite different cross section. They're so-called vertical transistors, but the principle of operation is the same, so that doesn't change. These are made to control many amperes of current, and usually have threshold voltages that are much higher than 1 volt. So these and they can stand drain source voltages that are up to 100 volt in some cases, even more. So these are really for switching power, and these are for amplification, for amplifiers and logic. One thing that should be noted is that because field effect transistors have these gates with these very thin oxides, they're extremely sensitive to overvoltages. So if you apply too much voltage to the gate of a transistor, you can easily destroy the device with a breakthrough, a breakdown from the gate through the oxide to the channel. And this is especially true for integrated circuits where the gates are extremely thin. So first of all, you need to be careful when you handle these. So you need to make sure that you're not charged up yourself when you touch these devices. So these electric charges appear when you walk around and your soles move over the floor. Then you can charge yourself up easily, and maybe you know the effect when you touch a door handle in winter. You sometimes get a small electric shock, and if that happens to your transistor, then it's probably dead. So that's what you can do. Make sure that you are not charged when you touch your devices, or don't touch them at all, at least not the contacts. And the other one thing is that usually circuits, especially integrated circuits that have field effect transistors, have input protection. So there's certainly a resistance between the input and the gate to limit the currents, but you also have these diodes, one going to the negative rail and one to the positive rail, making sure that this point here, or this cannot go beyond the positive or negative rail. So if you try to pull this one higher than the positive supply voltage, then this diode will start conducting and make sure that this node does not go beyond the supply, and this protects then the gate. The same goes in the opposite direction here. So this is built into most integrated circuits, but still one needs to be careful with field effect transistor inputs. Okay, let's look at the IV curves of a power MOSFET in this case. So these are typically packaged like this. You have something that can dissipate the heat. These metal pieces are then take away the heat. So these are relatively long channels, and they have basically ideal saturation characteristics. So in this region, you see no early effect. So these are very ideal transistors. So this really looks like the simple theory that we've introduced in the beginning. These have relatively high currents, so many amps for this one in this case, and they also have relatively high threshold voltage. So here, to get some conductance, you need to apply more than 6 volts of a gate voltage. This, of course, varies from device to device, from vendor to vendor. So if you buy the same transistor with the same name from 2 different vendors, the threshold voltage may be different. So you need to look at the data sheets here. what is typical for these power MOSFETs, but also for many other transistors, field effect transistors, is that bulk and source are connected here. And if you look at the cross-section of a transistor, that means that you now have a PN diode between the source and the drain, which is called the body diode. So this is sometimes explicitly drawn. And so you have to look at the transistor as this thing here, where you have this additional diode here. This plays a role sometimes and must sometimes be taken into account. On the other hand, if you look at a small transistor from an integrated circuit, so here's from a 250 nanometer channel length transistor NFET, you have much lower supply and threshold voltages. So this is typically 2 volt supply voltage, and threshold voltages in of the order of 0.6 volts. And the IV curves are not nearly as ideal as they are for the larger transistors. So there are a number of small effects here that need to be into account, which we don't go into. And they're quite complicated. And if you really want to make a quantitative analysis of such a circuit, then the best way is to use SPICE. So the SPICE models for these transistors are very complex, but allow extremely accurate simulations. So this is like an overview or a comparison between the NPN and the NMOS. So we are talking in the case of the NPN now about the active region, which is similar to the saturation region for the NMOS. So the NPN is controlled by the base emitter voltage, and the NMOS is controlled by the gate source voltage. And as a function of these voltages, you have this steep exponential curve for the current, for the NPN, for the bipolar, and this slightly less steep quadratic curve for the field effect transistor. So the principle of operation, the physical mechanism is very different. So here you have diffusion of minority carriers. Here you have the drift of majority carriers after inversion, I should say. Then you can view this transistor either as current controlled or voltage controlled, and what it is really depends on the impedance of your signal source. You know, if you have a very low impedance signal source, then you can also operate a bipolar transistor as voltage controlled. But if your output impedance of the signal source is rather high impedance, then the small input resistance of the bipolar transistor then basically makes this a current controlled device. The field effect transistor, on the other hand, is always a voltage controlled device because there's no appreciable DC current into the gate. So this is this line. So you have a small input current here into the base, which is then amplified to a proportionally much larger current from collector to emitter, while here you have no input current. I already mentioned the exponential curve, which is a quadratic curve. So here your gate voltage must be always, or your gate source voltage to be precise, must always be higher than the threshold. This is where this starts. And here you have this effective threshold, which is typically of the order of 0.7 volts, which comes from the steepness of this curve. So if you want to operate a bipolar transistor as a current source, then you must make sure that the collector emitter voltage is higher than the base emitter voltage. And similarly, if you want to operate a current source in saturation as a current source, then the drain source voltage must be higher than the difference of gate source voltage minus threshold voltage, which is basically when it's on. There's one small complication here. That's the early effect, which is for the bipolar transistor, the base width modulation, and very similarly, it's the channel width. Channel length modulation for the field effect transistor, and everything, of course, correspondingly for PMOS and NPN. So before we look at the high frequency behavior of these transistors, we also need to look at capacitances, as we did for the bipolar transistor. And obviously, source and drain have capacitances from their junction here to the bulk. But the most important capacitances are capacitances of the gate. And the largest and most important part here is the gate to channel capacitance. So if you look at the gate, it has some capacitance to both source and drain, and the sharing depends on the working point. So if you're in the strong inversion case where the channel basically is uniformly charged, then the sharing will be equal. So you have the same capacitance to the source and the drain. But when you're in this saturation mode, then most of the capacitance really goes to the source, because on this side there's less charge in the channel, or it's higher resistance. So roughly the sharing is like this: that the gate source capacitance is 2/3 times the width times length times the capacitance per area of your gate. And this is typically much larger than the gate drain capacitance. And so this gate capacitance can be substantial. It's from femtofarads in an integrated circuit up to many nanofarads when you look at the power MOSFET. So when you drive the gate of the power MOSFET, this can be a substantial capacitive load. What does that mean for the high frequency behavior? Here we can do something very similar to what we looked at with the bipolar transistor. So this is the small signal equivalent circuit of a bipolar transistor at the top. So here we have base emitter voltage controlling the current source here. You have the input resistor and the output resistor, which is due to the early effect. And we have the capacitances from the base to collector and emitter. And basically the same for the field effect transistor. Here the drain current is then modulated by the gate source voltage. There is some output resistance due to the channel length variation, but there is no input resistance here, because there will be no DC current flowing into the gate. So we can again look at what happens when we go to high frequencies now, and try to see what is the effect of these capacitances here. So let's apply an AC voltage to the gate of an NFET with a grounded source. So there's no DC gate current, but when you apply an AC current, then due to the capacitances, there will be an AC current here. This is here. This you can also see here from the small signal picture. And we define the AC current gain similarly to the bipolar transistor by the ratio of the drain current as a function of frequency divided by the gate current as a function of frequency. And here we neglect the output conductance. So let's look at the current balance in this node. So you have the drain current here is equal to the transistor action, so GM times the gate voltage, and minus the current that flows through this capacitance, which is gate source voltage divided by this impedance, and the impedance is 1 over I omega C. So this is the current balance in this node. We also need the current balance here, and there the current from the source here simply flows to these two capacitors in parallel. So we have I omega times the sum of the two capacitors times the gate source voltage. The ratio of the two is then simply this expression, so Gm minus I omega, because V gate source cancels here. So it's Gm minus I omega C gate drain, which is, as we said, the smaller capacitance divided by I omega divided by the sum of C gate drain and C gate source, which is the more important term here. So again, we can make a Bode plot of this, which looks similar to what we had for the bipolar case. The only difference is that this will never become flat. So for the bipolar transistor, at some point you have a constant value here, which is the DC current gain. So that doesn't happen for the field effect transistor, because there's no DC current. But you have the same 1 over F, 1 over frequency fall off for sufficiently high frequencies, where you can neglect these terms most of the time, and you simply have GM over omega times the sum of these capacitances. And sorry, the frequency where this current gain dropped to 1 is called the transition frequency, similar as we had it for the bipolar transistor. And this transition frequency is the value of this transition frequency is then simply GM divided by the sum of gate drain and gate source capacitance. So that was, of course, the angular frequency. So the real transition frequency is defined as 1 over 2 pi multiplied by the angular frequency. So you get an extra factor of 1 over 2 pi in front of this factor here. And this value for silicon MOSFET is typically in the region from gigahertz to hundreds of gigahertz. We can plug in what we learned about these transistors. So the GM is the mobility of the charge carriers times width over length multiplied by the oxide area per unit, oxide capacitance per unit area times the difference of gate source and threshold voltage, while the rough estimate for the gate source capacitance is just the capacitance of the gate, which is width times length times capacitance per unit area. So the ratio of the two here is roughly so GM over CGS, which dominates, is then mobility times the voltage difference divided by the length squared. So the channel length appears with the square here. So it's clear that if you want fast transistors, you want to have your channel as short as possible. And that's one reason for going to smaller and smaller transistors, of course. On the other hand, you also want, in this case, a high mobility. So the fastest transistors also use technologies that offer the highest mobility. So in normal silicon, the NFET is preferred for high transistors, for high mobilities and high gain, high frequencies. But there are also some specialized technologies that try to increase the mobility of the carriers in the channel to get faster transistors. And it's also true that in this case, this transition frequency is related to the time that the carriers actually need to the inverted channel. So the last effect that we want to look at briefly now is the body effect or backgate effect. So far, we haven't discussed what the bulk potential is. It was usually taken to be 0 or the same as the source potential. But there is a small effect. Basically, the bulk potential modifies the threshold voltage. So this forms effectively a second gate. So you don't only control the charge here through the gate voltage, but also through the potential of this bulk, and this is sometimes called a backgate. The potential here must always be negative with respect to the channel, otherwise these become conducting, as we said before. And the modulation here, so how much it affects the charge in the channel, is much smaller than the capacitance from the gate. So here you have this extra thin insulator to make the capacitance larger, to make the modulation large. But here you have this depletion region between, so the capacitance is much smaller. So the modulation from the back gate is much smaller than the modulation from the front gate. In most cases, this is not used to modulate really because it is less, and it also brings a huge capacitance. So you cannot really use this terminal as a second gate to your transistor. So it's in most cases it's more a nuisance than it really is a feature. Okay, I think yes. So let's take our break here, and then we continue with application of field effect transistors. So I would say we continue in 10 minutes at 2:45. Okay, so welcome back. Let's continue with field effect transistors. So we learned about this new type of transistor. Um, Fortunately, we don't have to go through all types of circuits again. So most of what we learned about circuits with bipolar transistors can also be applied to field effect transistors. So switches, followers, current mirrors, and amplifiers. In most cases, or in many cases, you can just basically do the same circuit with a field effect transistor that we did with a bipolar transistor. So there's a bit of a cheat sheet here. So whenever you use an NPN bipolar, you should use an NMOS field effect. A PNP is used as a PMOS. And of course, instead of emitter, collector, and base, you now have just different names: source, drain, and gate, due to the different physical processes here. And wherever you use GM for the bipolar transistor, you also use GM for the field effect transistor. However, there's no equivalent for the current amplification beta because there's no DC gate current for the field transistor. On the other hand, the bipolar transistor does not have a bulk connection as the field effect transistor does. Now, probably in practice, you will not build many circuits with more than one or two discrete transistors in MOSFET, but probably also not in bipolar either. What is more likely is that you combine these transistors with integrated circuits that you buy commercially or get elsewhere to give them special properties for high frequency or high power and so on. Or on the other hand, if you design your own application-specific integrated circuits, the ASICs, which is not as crazy as it might sound. So in that case, you will use many transistors. And field effect transistors allow much higher integration density than bipolar. So that's why they completely dominate the digital market. Analog integrated circuits, on the other hand, exist both in bipolar and field effect, and also combined processes where you have both field effect and bipolar transistors in the same chip, so-called bi-CMOS chips. As an example of something that can be done basically the same is the emitter follower with a bipolar transistor, or source follower as it's called with the field effect transistor. It's the same circuit where you replace your NPN with with an NMOS. The main difference here is that typically you have a higher output resistance for the source follower because the IV curve is less steep than it is for the bipolar transistor. But the advantage is that you have a much higher input resistance, so there's no input current at all at DC. Here we look at the behavior of a source follower with a 250 nanometer gate length and FET. So you see here as a function of the gate voltage, the input, showing both the gate voltage, which is of course simply the diagonal here, and the output voltage. And as soon as the input voltage goes above the threshold voltage, or near the threshold voltage, the transistor turns on. And after that, it follows almost linearly with an offset that is slightly larger than the threshold voltage. So this behavior is very similar to what you get with the NPN transistor, with a bipolar transistor, maybe slightly less ideal. Now this transistor has the bulk connected to the source. If you connect the bulk instead to ground, you get the blue curve here, which is significantly worse because now you have this body effect. So the back gate counteracts the modulation of the input a little bit, and you get this much less steep curve here, which follows with a slope that is much less than 1. So for a follower, for a source follower, you would ideally connect the bulk to the source if you can. Sometimes it's not possible. The other thing that you can also do, maybe surprising at first because there's no gate current here, but you can use them very well as current mirrors, because the gate current really is just a nuisance for the base current is just a nuisance for the bipolar transistor. The principle is the same. So these two transistors have the same gate source voltage, so the current is essentially the same. And if you have one of these transistors with a long channel that has almost no channel length modulation, then this is basically an ideal current mirror. What is of course crucial is the matching of these transistors, as it is for the bipolar transistors. So bipolar transistors, especially discrete ones, the matching is usually terrible. For the field effect transistors, can be much better, especially in integrated circuits, where the matching is often improved by certain layout tricks. So if you want two transistors to be good current mirrors, you make sure that they are really drawn in exactly the same geometry and not too far away from each other. You give them large gate areas to have as little as possible statistical fluctuations or other fluctuations in the geometry. And one can also make compensating arrangements. So you make 4 transistors instead of 2, and you try to arrange any changes that appear across the circuit from fabrication or from temperature to compensate as much as possible. And then you can get really good current mirrors in CMOS, much better than in bipolar. Another important application for discrete transistors, for discrete MOSFETs, is switching. The advantage of power MOSFETs, there is an advantage of power MOSFETs for switching large currents, because the base current in a bipolar transistor is not always negligible. So if you want to turn on some device here that is connected to the positive rail here, you have to bring up the base, and there can be a significant current that flows into this base, and your driver must be able to deliver this current. While on this side, you can just turn it on and without delivering any current to the gate, except when you turn it on, you have to charge the gate here. So this means that even large field effect transistors can be driven directly by digital logic. However, you must make sure that your digital logic goes high enough to go above the threshold voltage of this transistor, of course. In both cases, you will often need additional resistors. In case of the bipolar transistor, to limit the base current. So these can be substantial when you're switching a large current here. Then you may need a significant base current, or if you go to the full swing of your logic here, then that's of course much too high, and you will saturate the transistor, and you need to limit current that flows in. So there will be usually a series resistor here. On the other hand, for a MOSFET, you have to make sure that the potential at the gate is always controlled. And many outputs, digital outputs especially, are often can be switched into a tri-state mode. So they're not just on or off, but they can also be in a disconnected mode. And then you must make sure that your device here is pulled to ground. Yeah, the gate here is pulled to ground. Otherwise, what this transistor does is completely undefined, and then you'll have a device that suddenly turns on, although you don't want it. So this you must take care of. Otherwise, you can then interface your Raspberry or whatever directly to switch large currents using a field effect transistor. Another interesting thing you can do with these is to use them as a mechanical switch or a relay. So if you have 2 signals that are, let's say, at similar potentials here, if you pull the gate to 0, this is an NFET, which you can see from the arrow going towards the channel. So if you pull the gate to 0, then the switch is off, and if you pull the gate to the positive rail, then the channel is conducting, the transistor conducts, and this will work either way. So when the input is slightly higher than the output, then the current will flow from the left to the right, and if the input is slightly lower than the output, then the current will flow from the right to the left. in order for this to work, you don't know at the point where you design your circuit where these potentials are. So you must pull the bulk, of course, then to ground to make sure that you never get into conduction with the implant to bulk diodes. And it's also clear that the name drain and source in this case are purely I mean, they don't really mean anything. So you do this with a symmetric transistor, and then the drain and source really switch role here. And this is something that you cannot do with a bipolar transistor. So this is really in the domain of field effect transistors. Now the problem here is when the input and output potentials are close to zero, this works very well. But when input and output potential go very high, especially when they go close to the supply voltage, then the difference between source drain and the gate becomes less than the threshold voltage, and this switch stops functioning. So this type of switch with an NFET will only work for in-out potentials that are not too far away from zero. So if you need to switch something that is at a higher potential, you need to add a PFET, and this is shown here. So the resistance of this switch, the NFET switch, deteriorates if you go up in your potential because you go closer to you decrease your gate source voltage, and the body effect goes on top of that. So you add the additional PFET, but you must then, of course, make sure that you control one with a voltage that goes from zero to supply voltage, and the other one must do the opposite thing. So to turn on the PFET when you turn on the NFET. And now this shows exactly the opposite behavior. The PFET will conduct better when input and output are close to this positive supply rail. So, and the combination then gives you good conductance all the way through. So this is called a transmission gate, and can be used like a relay, or sometimes called a solid state relay. These you can, for instance, buy packaged with multiple such switches in one package for parallel multiplexing. Another important application of such transistor switches is sample and hold circuit. So when you use the field effect transistor and a capacitor to memorize the value of a voltage that changes over time at a certain point in time. So you want to know what was the voltage at the time when I flipped the switch. So you have this the varying input signal here that goes through the switch, and the value is stored on this capacitance when you open the switch. So you can freeze the value at some selected time for later processing. For instance, then you turn on your ADC and digitize the value, or you do some other analog processing. One small detail here is that the moment you close the switch, you apply a voltage step here on the transistor, which will, through the capacitance of the gate, also affect the voltage that is stored here. So you'll see a small jump here in the voltage, but after that is constant. This is not such a real problem because the size of the jump is usually constant, and you can correct it later. But it may need to be taken into account. And this is also partially compensated when you use transmission gates, because there the jump has the opposite direction for the PMOS, which would be on the other side, and it's not shown here. Okay. Unfortunately, there are several types of field effect transistors. So far we only talked about this type here, which is called enhancement mode or normally off. They have positive threshold voltages. The symbol is this one here, where you have the channel shown here with these little breaks here, which is trying to indicate that there's no channel when the gate voltage is zero. So there are different versions of this. So either you have relatively high thresholds, then you have a very small leakage current and can switch large currents. These are the power switches, or you have very small positive threshold voltages that are used in low power electronics and digital electronics. But there's also a version of the field effect transistor where the threshold voltage is actually very small or even negative. And these are called depletion mode or normally on transistors, then the symbol is slightly different. So here the channel is drawn as a continuous line, trying to indicate that these transistors are really always on unless you pull the gate to a negative voltage. There's yet another type of field effect transistor, which is called the junction FET or a JFET, where the gate is not formed with a metal layer and an insulator, but a PN junction instead. So these are always in depletion mode, so there you always need to do something to switch them off. They have a small non-vanishing gate current, but of course it's much more smaller than it is in the bipolar transistor case, not base. Okay. Oh no, base is correct. But most transistors that will use that you will see are in this category. Okay, finally, let's talk a bit about logic and CMOS. So only some very low-level stuff. If you want to know all about digital electronics, there's the follow-up lecture by Yves Ackermann in the spring semester, Electronic for Physicists 2. So in logic, logic states are represented by electric potential. So there's a 0 and a 1 represented by low voltage or high voltage. And then usually in between there's of course a transition which should not appear. So the output of a circuit should be well defined, either high or low. So then you have some circuits that implement logic functions, so-called logic gates. So you have a number of inputs here and an output that is a function of these given by some truth table, and this is then of course implemented with transistors. So let's start with the simplest one here, which is the inverter or NOT gate. So the truth table is very simple. If the input is 0, then the output should be 1, and if the input is 1, the output should be 0. This is the symbol. It's like an amplifier, but the little circle here indicates that it inverts. So and then in logic, you will also often see other symbols like this one, for instance. I prefer this one. And the simplest implementation of this is if you have a transistor with a resistor. So you treat the NFET as a switch. And you could do the same also, of course, with a bipolar transistor. And this was, in fact, the first logic family that has been used widely was with bipolar transistors that were invented before the field effect transistors. And this was called resistor transistor logic, RTL. So when this transistor is off, there's no current flowing, and the resistor will pull this node up. When you pull the input high, the transistor turns on, and there's current flowing, and this node goes down, so the output will be low. Now, this has the disadvantage that there's always a continuous current flowing when the transistor is on, which causes some power dissipation. And this can be avoided by replacing this resistor by a second transistor of the inverted polarity, the PMOS. So you have an NMOS and a PMOS. And since you use both technologies here, the NFETs and the PFETs in one chip, this is called CMOS or complementary MOS. And this is the vast majority of all logic that you will see these days is in CMOS for complementary MOS. So how does this work? So when the input is high, the NFET gate is high, therefore the NFET is off, while for the PMOS here, the gate source voltage of the PMOS is 0. So the PMOS has the source up here. So this transistor is off. So all you have here is the NFET pulling the gate down. So once you have a 1 here and a 0 there. The opposite case, when you pull the gates to 0, then the NFET is off because its gate source voltage is off. The gate source voltage on the PFET, for the PFET, on the other hand, is now maximal. So this one is all the way on, and it will pull this node up. So you get a 1 on the output. In both situations, there's no static current. So this is a very power efficient technology. The only current flow happens during the switch over. So in the transition from 0 to 1, you will have a current that flows. And in the in the static case, when you just hold a logic state, there's no static current. This is, of course, for the ideal case that we have no current flowing when the transistor is off. Unfortunately, very short channel transistors have non-negligible leakage current. So here one has to take care um, that these leakage current don't destroy your power budget or have other effects. So this slide shows three views of an inverter. The first one is the circuit diagram that we've just looked at. So there's an input going to the gates of a PFET and an NFET, and usually you have some capacitance that is unavoidable from interconnects or to whatever is connected here. If you look at it as a cross-sectional view from for the field effect transistors, so here you have the NFET, everything is in a P substrate. You have the N implants for source and drain, and there's also a body contact here. The PFET must be in a P substrate, in an N substrate, which is usually then by putting an N well into the P substrate and then make the implants for the transistor here. Sorry, make two P implants inside the N well to form your P transistor. And this here symbolizes the metal gate across the channel of these. If you look at the same thing now from the top, this is shown here. You have the NFET at the bottom and the PFET at the top. The PFET is larger in this case because you need a wider transistor to get the same drive because of the low mobility of holes. So the NFET can be made a little smaller and is equally strong. So the gate is shown here. It connects to both transistors. The channel is now basically going perpendicular here to this gate from source to drain, and the same thing here from source to drain here. So and this part will be connected to the supply voltage, and this one will be connected to ground. And here's the output, which is the common node of these two transistors. So this is the simplest possible gate, the NOT gate. You can also do more complicated things like the NAND gate. So a NAND gate is the end of A and B followed by an inversion logically. But it's usually implemented not as an AND, but as a NAND, because that can be done with a simple combination of 4 transistors. So you have 2 NFETs pulling down, and they will only pull down if both NFETs are switched on. So if both A and B are high, then these 2 transistors will pull down the output node. And if either of them is low, then the PFET here will be turned on, either A or B or both, and pull this node up. This is shown here. So only if A and B are high, you will get a 0 at the output, and if either A or B is low, the output will be high. This is called a NAND gate, and this shows a possible layout for a NAND gate. So you have the 2 NFETs shown here at the bottom, shown basically in the same substrate here. So this node here, which has no connection, is not even contacted here, of course. Sorry. So the gates can just follow each other in the same tub, and the output node here is also connected to the point between the 2 transistors for the PMOSs up here. Okay, but let's go back to the inverter and take a look at how this works dynamically. So this shows a simulation of an inverter that gets a square wave input. The red curve here, the black curve shows the input going up and down. And we look at the output, the red signal, and you see that it switches very fast, so much faster than a nanosecond for these transitions. And you see these small voltage spikes here. These are from the capacitive coupling of the gates into the outputs. Now, in the real world, there's always some capacitance from either from wires or from the inputs of the following gates. And this reduces the switching speed. So we still have the same square wave input here, but the output now gets this RC-like behavior. So it falls off with a certain time constant before it reaches the new value, and so on. And so this is the current that needs some time to charge these capacitors, and charging these capacitances also consumes power. So um, uh, so the charge is capacitance times voltage, and so the work that you do is then another factor of the voltage. So you have the supply voltage squared times the internal capacitance, and if you do this with a certain frequency, there's also for the power you get a frequency factor here. So CMOS chips, although they don't have uh, a static current in the ideal case, they have a very high dynamic power consumption due to the switching, which is proportional to the frequency and the supply voltage squared. So if you want low power electronics, you try to go to lower supply voltages. Now let's look at a chain of such inverters. Now each inverter is the is the capacitive load to the one before, and the time delay in such a chain determines, so to speak, the minimal switching delay, which tells you how fast such a chip that is made out of such transistors can work at all. And in this case, you can read off from this diagram. This shows the output of the. So here's the input to the first one, and then the outputs of the following ones is delayed by roughly 100 picoseconds per two inverters. So for one inverter here, you have a minimum gate delay, a so-called gate delay of 50 picoseconds. Obviously, when you have more complex gates like NORs and NANDs and so on, these are slower than just inverters. And so processors that are in such a technologies a couple of years ago ran up to 400 megahertz. If you change the supply voltage, the time to charge these capacitances actually increases. So you might think it goes down because you have to charge them to a lower voltage, and then you need less time with a certain current. But the current that comes out of a transistor also changes as a function of the voltage because the gate source voltage varies. So the net time, and it varies with the square of the voltage. So the net time that you need to switch from one cycle to the other actually goes up if you decrease the supply voltage. So with a lower supply voltage, your circuit becomes slower. So modern processors, you may know, change the core voltage according to the required speed. So if you don't need to run as fast, they simply change the voltage to save power. This can be used, this effect can be used in other ways. If you take now such an inverter chain and connect the output of the last one back to the first one, and the number of these inverters is in odd numbers, then well, you might think you have a static situation where the input and the output are equal to half of the supply voltage, but this is not a stable situation. And as soon as one of them starts tipping over, this propagates through this chain of inverters and comes back in the end. So what you get here is an oscillation, which is quite similar to what we've seen in these high gain amplifiers with feedback, but this is extremely nonlinear. So these don't make a sinusoidal oscillation, but they immediately ramp into saturation up to the supply voltage. So now what you have here is a so-called ring oscillator, which oscillates with a frequency that is given by the minimum gate delay here and the number of inverters in the ring. And as we've seen, the gate delay is a function of the supply voltage. So if you change the supply voltage for such a ring oscillator, you can change the frequency of oscillation here. This is shown here. So for the highest supply voltage, you get a fast oscillation. And if you change the supply voltage you can reduce the frequency. So such a circuit that can oscillate with different frequencies as a function of the voltage that you apply is called a voltage controlled oscillator, or VCO. And normally, or for extremely high frequencies, these are done with LCs using controlled capacitors, for instance, as we've seen with the varactor diode. But up to gigahertz frequencies, as they appear in many applications, this can also be done with a voltage-controlled oscillator of this ring oscillator type, which is nice because then you can directly implement it in your integrated circuit. So an important application of such ring oscillators or voltage-controlled oscillators in general are the so-called phase-lock loops, where you take an input signal that is periodic or more or less periodic, let's say, and you try to create an oscillator that oscillates with the same frequency as the input signal, which you may not know a priori. So then you need a so-called phase detector, which takes the input signal and the output signal of your VCO and compares the two signals and decides which one is ahead of the other one. And if the input is ahead, then you increase the voltage to make your oscillator go faster. If the output is ahead, you decrease your voltage to make your oscillator go slow. And this way you can create a signal that is locked in phase to another signal. And these are used in many circuits for demodulating signals where you have a carrier frequency with some information modulated onto it. But you can also use this to remove jitter when the phase of this signal has some noise on it, which you need to get rid of. Then these PLLs can be extremely stable and create very jitter-free oscillations from an input clock that has jitter. But you can also use them to do frequency modulation, so frequency multiplication. And that is shown here on the next slide. This is an example from a chip that was made in our group at some point. So you have an input clock which had, in this case, 40 megahertz. This is a phase detector, which consists of two flip-flops, basically, which so this just decides which of the signals came first, either the one from the input or the one from our controlled oscillator. And then if this one was first, then it sends a current into these capacitors, bringing this voltage up. And if the other one came first, it pulls a current out, bringing this voltage down, and thus controlling this voltage-controlled oscillator. And then if you don't feed back the signal directly, but you divide it by 2 using basically a 1-bit counter or dividing it by 4, then you can actually achieve a frequency multiplication. So now you come out with 160 megahertz that you generated from these 40 megahertz, and they are locked in phase. So this is called a phase lock loop, or PLL. Now let me spend a few minutes talking about microelectronics and particle physics, because this is what we do in our group. So in order to use microelectronics to detect charged particles, one thing that you can use is a PN diode operated in reverse bias. This is shown here. So this is basically a large PN diode. So you have the for instance, the N implant here and a P implant at the backside, and in the middle you have a region with very low doping. So when you apply a bias voltage across this diode, you get a large depleted volume here. And when a particle flies through such a depleted volume, it occasionally knocks out electrons from the valence. It knocks out valence electrons from the silicon atoms in this depleted volume. And because there is an electric field here in this volume, these electrons will be pulled away from the track and will be collected at these electrodes, the P and the N side. So you collect the electrons here and the holes on the other side. And this produces then a short current spike. So whenever a particle flies through our detector, we see a short current spike, and this needs to be amplified. And in order to do this, we connect this part of the diode with an integrated circuit that contains an amplifier. And this is symbolized here. So you have these are the transistors that you have in your readout chip, and they form an amplifier that amplifies the current spike, and this can then be read out uh, uh, to find particles. So just to show an example of something that was built at PSI, is the CMS pixel detector. So you have many thousands of these in a single chip. They are arranged in this way here, that they cover an area with these rectangular arrangements, and all these pixels in the detector must be connected to the amplifiers in the readout chips using this so-called bump bonding. So these are little indium spheres or lead spheres in some cases that are used to make the connection between the sensor and the readout. And then this forms larger elements, larger detector elements, which are then grouped into certain layers. So here you see a 4-layer detector, and the innermost layer is shown here. The beams at the LHC will go through the middle of this. This is just the lower half of the detector. The second half would be on top of here, and the beam goes right through the middle of the detector. So this has pixels of 100 by 150 micron squared size, and hit rates of more than 100 megahertz per square centimeter. The reason why these need to be bought and need to be made for ourselves, and you cannot just buy them. For instance, something similar as we do is done in CMOS cameras, but CMOS cameras will not work because they're not radiation hard. So these chips get a lot of radiation and must be designed in a way such that they withstand this. And this detector was operated for many years, and will still operate for several years in the CMS experiment at the LHC. And this is what this looks like. Here you see the detector planes where the tracks of these particles are detected, and this shows let's say a typical event, and each one of these lines is a particle flying through, and they're detected here. And then if you measure the intersection at these detectors, so you have these points here, and from the points in many layers, you can detect the track of the particle and point it back to the interaction region and see what happened here. And this is what we're doing at the CMS experiment, to analyze this data and reconstruct the collisions of protons here in the center of our detector. There's more development going on at the moment. So this detector has been built and is being operated now. And for the future, we're trying to use the CMOS wafer itself as the sensor. So the principle is the same. So you try to use the bulk of the silicon of the field effect transistor as your sensing element. This is very similar to what CMOS cameras do, in fact. And this shows a prototype chip that has been designed by Stefan and was just submitted. So this is the full test chip with an array of pixels. This shows a detail, and if you zoom in even further, then you can see individual transistors here. So this is, like I said, basically Stefan's PhD thesis, and I would just like to do a small commercial break here. So if you think electronics would be interesting for you, and you like possibly also particle physics, then we usually have opportunities for students to do work related to microelectronics in particle physics. Okay, so a bit of an outlook. The field effect transistor is evolving. So it was invented maybe in the, let's say, in the 60s, 70s. And since then, there has been a continuous development. So as a function of years, the gate length was reduced. So this is the blue curve from several microns down to now the next generation. The smallest transistors are in the nanometer region, a handful of nanometers. But processes that have hundreds of nanometers are also still around and are being used, because not everybody needs these extremely small gates. lengths. So with the gate length and the overall feature size, also the supply voltage is going down. So the earliest CMOS processors had supply voltages of 15 volts. This went down to 5 volts, and now we're well below 1 volt in the most modern technologies here. On the other hand, the number of transistors per chip, as you know from Moore's law, went up and up and up, and still seems to continue to increase exponentially. So we come to our summary. Field effect transistors can be used in very similar ways as you can use bipolar transistors. So everything you learned about circuits with bipolar transistors, or most of that, applies to field effect transistors. The main difference is that there is no gate current, but you can have, for large transistors, a substantial gate capacitance. So digital circuits, digital ICs are completely dominated by MOSFETs or CMOS to be precise, while analog circuits use both bipolar and field effect. Now for the highest integration density, people are now moving away from the planar MOSFET that I've shown you in the beginning, because the leakage current becomes a real problem. And when you go to such small structures, and when you have more 3D-like structures where the gate goes all around the channel, you get better control of the channel by the gate. So these are the so-called FinFET transistors, for instance. So here the gate is perpendicular to this material between source and drain. So the channel is all this material, and the gate goes all around. It's not just sitting on top of it. And then taking it a bit further, then you get to the ideal transistor, which is like a circular object with the gate going all around the channel. And this type of transistors are standard now for everything below 22 nanometers gate length, which are the modern transistors that you can buy these days. Okay, that's it for transistors. Thank you for your attention. And next week, Georg will continue.